Let's talk about hybrid orbitals today. So a hybrid orbital is any orbital that is going to hybridize in order to bond with another element. So atomic orbitals are divided into different suborbitals, S, P, D, and F, and so on. And what happens is when they do a bond with each other, they begin to combine electrons and share space. Now you need to know the names of these types of hybridals and what type of angles they produce based off of these electrons. So let's go ahead and dive in here. So let's give you an example. If I have a charge cloud around the central atom of how many charges around them, you're basically going to have an S and P. And usually the bond angle is going to be a 180. Now the great example of this is if you take a look at carbon dioxide, is these charge clouds are basically how many attachments you have. So I have two attachments. So if I have two attachments to the carbon, for example, oxygen and oxygen, you're going to end up with two around that central atom. And what you're going to first have to do is figure out what the number of charge clouds to figure out what the hybridization is. So if you take a look at that, usually it's going to be an sp hybrid orbital because you're going to utilize the S and the P. And the bond angle here is going to be a 180-degree angle. Now what if I have three things attached to it? Now if I have three things attached to it, I will be using an sp2. So one for the S and then two for the P's, and that's called an sp2 hybrid, or we'll call it the 120 bond angle. And this actually corresponds to bond angles once you start looking at the geometries. Now if I have four things attached, for example CH4, then you're going to take one S for the H's, and then you're going to end up with four identical sp3 hybrids. So a CH bond is going to form four sp3s of equivalent sizes, and they're each going to be worth 109. As you can see, the bond angle decreases the more attachments we have. So generally speaking, when you're talking about hybridization, you're really talking about sp hybrids. So, if you're taking a look at things like carbon attached to a hydrogen, and hydrogen has an S shell, and also the carbon has an S shell with a P shell, the S and the P are going to automatically lump them up together. Now here's a classic example of a double bond, which is C2H4. In this specific case, each carbon, and we always look at the central atom and how many attachments it has. So in this specific case, carbon is attached to hydrogen here and a carbon, and they have what they call three charge clouds. One with the carbon, one with the hydrogen, and one with the hydrogen. And these are called sp2 hybrids, which means that every single time you have that carbon in there, you're going to have these three attachments. So carbon is going to go ahead and attach itself to the carbon with an S and a P. Same thing with this carbon right here. It has sp2 hybrids, which means you're going to have three charge clouds as well. Now, if I actually wanted to draw the sp2 hybrids, how would they look like? Generally speaking, we're going to talk about them in terms of sigma bonds and a pi bond. The double bonds consist of one sigma and one pi bonds. So if we take a look at the back of the example right here, you're going to have an sp2 and you're going to have this specifically configuration. So the hydrogens are attached to the sp2s, you have your P's, and then each one's going to have four attachments compared to that. And so that kind of brings us to this idea of sp2 hybrids, is between the carbon, since carbon has P2 and S2, what ends up happening there is you're going to hybridize with the hydrogen to create those sp2s for each one. So that's basically generally how we kind of look at it from that direction. There's also specific cases which have to do with cis and trans isomers, and these have to do with sigma bonds. They're able to spin on the axis, either one up and one down. So usually, like I said, for double bonds, we're usually called pi bonds. You're going to be spinning on this axis. And so here's an example of something, a hydrocarbon that has what's called cis-2-butene. In this specific case, it follows a carbon chain. You can have the two CH3 groups at the very top, which are cis, and trans, meaning that they're on opposite sides. And this is C2-butene, meaning that it's indicating which carbon it actually has that. Now for triple bonds, a little bit different story. Triple bonds have C2, like for example C2H2. This one has two charge clouds, and these are called sp hybrids because they're linear. So again, it kind of really depends on the geometry to tell you whether it's going to be a one or two charge clouds. Now in this specific case, a triple bond is going to contain 1 sigma and 2 pi bonds. So what you're having here is sp hybrids going around with each other along with the p's, and then they're basically going to be in a linear form. Alright, and here's something a little different when we're talking about p orbitals and overlaps for the benzene ring. As an example, you have CHs, each corner is a carbon, it's a carbon with a hydrogen bond each other, and then they're going to end up overlapping. And so usually what happens is that if you want to draw these structures, you draw them as a delocalization of electrons, which means electrons are circling around the benzene, and because of that, they're going to end up having resonance structures because of that, because you can actually arrange the double bonds in this way or this way.